elevators. So I will try to do a picture of the elevator here, but my drawing is not the best. So the way that the elevators work, here is the cabin that the elevators or people go in, and then we have like a bunch of strings here that the elevator is tied with, and then a pulley system that it makes it go up and down, and then those systems are connected with an electrical panel that whatever floor you press, then they stop, and then the door of the elevator is open. However, what we will be seeing now is three cases: when the elevator is going up, when the elevator is going down, and when the elevator is moving with constant velocity. And then we will find the tension that the string is experiencing. So now let's suppose that the mass of the elevator with some people on it is 1,000 kilograms. And the first case, or the first situation, is when the object is moving with constant speed. So you probably have experienced being in an elevator, especially when you are dealing with a lot of floors. On the first moment, you feel that there is a change on the weight of your elevator because the elevator starts to move. Then as you start going up or going down, then you feel that the elevator is not even moving, because you are part of the elevator and the elevator is going at constant speed. So going with constant speed or constant velocity means that the acceleration of the object is equal to 0. So the free body diagram in this case will be something like this. The object of our interest is with a dot. So then we will have the universal force of gravity that is always toward the center of the Earth. And for simplicity, we will consider that there is only one string that the elevator is tied with, even though that this is not the case, because our security will be in a huge jeopardy. And we have a tension that goes along the string, from the object along the string. Now, it doesn't really matter if the elevator is going up or is going down. As long as the acceleration is equal to 0, it doesn't really matter, because on this case, what do we have is those two forces are equal to each other in magnitude and opposite direction. Why? Because the force net is equal to 0. And even if we do the table, so if we say that, okay, I will do the table for it, horizontal, vertical, we have force of gravity, tension, and force net. So horizontal, everything is 0 because the object is not moving left or right. It's just going up or down. Force of gravity is a negative mass of the object, which is mass of the elevator itself and mass of the people that are in the elevator times g. Tension is positive because it is on the positive direction of the vertical component. And force net, since the acceleration is equal to 0, is equal to 0. So even from the vertical, we can figure out that tension is equal to mass times acceleration due to gravity, which tells us that those two forces will cancel each other. And they will cancel each other because they are exerted at the same object. However, when we have a case when the elevator is starting to move up, so then we have an acceleration, and I'll just put a number here, 2.0 meters per second going up. Then what we will see is, in terms of the free body diagram, will be something like this. Force of gravity doesn't change because mass of the elevator with people on it will be still 1,000 kilograms. So will be mass times acceleration due to gravity. However, since we have now an acceleration that is going up, so the acceleration is going up, that means that even force net will be going up based on the second law of Newton. We said that force net is equal to mass times acceleration. So when we draw the free body diagram on this situation, the tension that the string will experience will be something higher than force of gravity. Okay, because what we have here in this case is from the vector's perspective. We have force net is the vectorial sum of all the forces that the object is experiencing. Since we are dealing with collinear vectors, vectors that are in the same line, maybe in the same direction or opposite direction, then we can say that force net is equal to negative Fg plus T, because negative because it is going down. Is it clear? Good. Now, from our relationship or our given in the problem, we have that force net is equal to mass times acceleration, that is going up on this case, and since it is going up, is positive. So now see what we have here. Tension is equal to mass times acceleration plus force of gravity, which is mass times acceleration due to gravity. So this is why free body diagram on this situation will be something in which is representing that the tension is greater than force of gravity. Okay. The third case is when the object is moving with an acceleration down. So now we have case 3, when the acceleration is a value, we will keep it as 2.0 meters per second squared, but now it is going down. It's going down. So then the free body diagram will tell us that force net is, so since the acceleration is going down, then this is telling us that force net as well will be going down. Why? Because we said when we talked about the second law of Newton that the direction of force net and the direction of the acceleration are the same. So now the free body diagram in this situation will look something like this. If this is the force of gravity that the object is experiencing, which is always starting from the object going toward the center of the earth, and it is in magnitude equal to mass times acceleration due to gravity, the tension will be a small value, or a small, representing a smaller value. Now let's do the table of components. So we have horizontal, vertical, force of gravity, tension, force net, 0, 0, 0, because in the horizontal is not moving. And on the vertical, what we will have is negative mg, because it's the opposite of the positive vertical axis, positive t, and here, since the object is going down, will be negative mass times acceleration. So from the vertical component of the free body diagram, what we will have is negative mg plus t is equal to negative mass times acceleration. So then tension will be mg minus minus mass times acceleration. So as you see here, even from those two relationships that we have on the screen, when the object is going up, accelerating up, tension is greater than force of gravity. And when the object is accelerating down, tension is less than the force of gravity. And when the object is moving with constant speed or constant velocity, I say constant speed just because it's moving in one direction, in collinear, up or down, the two forces are equal in magnitude. Okay, so now before we move to the next topic or subtopic of the elevators, we have to clarify something. When we see those scales in our homes, what they are measuring is actually the force normal that we are exerting to the springs of the scale. So the scale has a platform where you are stepping in, and then underneath there are some springs. And now we know that the force of spring is negative. It's the opposite of what is happening. So when you step into the scale, the springs will be compressed. Therefore, the force of spring will be opposite of the compression. So will be, if you are compressing it, this is X, then the force of spring will be the opposite. And this will create, after converting it, will give us the information how much kilograms we weight. Now, what we are doing, so pretty much what scale is that it's measuring force normal, okay? Is telling us what is the force normal. And when force normal of the scale is equal to force of gravity, then in a way is telling us how much kilograms we are. Now, what we are doing is we are putting the scale in the elevator, and then we are stepping into the scale and seeing how our weight will change into our weight will change into the scale. Now keep in mind what I said. I said weight, which is the vector quantity. If you have a scale that is measuring kilograms, then it is converting it into a scalar. But when we have a weight that is measuring in kilograms, which is a scalar, and we are putting it into an elevator that is accelerating up or down, then we will see a difference into the kilograms, even though that is like what, less than 1 minute, a difference on kilograms, because it is measuring the weight and converting the weight into kilograms. Is it? So we'll see the case when we are stepping into the scale, and again, case 1, we will start when the acceleration is equal to 0, meaning that we are at that middle part of the elevator where the elevator have started, and then it is moving with constant velocity, either up or down, doesn't really matter. Because when we have constant velocity, that means that acceleration is equal to 0, which is translated into force net is equal to 0. So what do you see in terms of the free body diagram at the scale in the elevator is that you have force of gravity that is always going down to the center of the earth. And here you have force normal because you are stepping into a surface. This surface is connected with some springs and so and so. So this is directly connected with the force of spring. So since force net is the vectorial sum of all the forces that the object is experiencing, then we can say that force normal is equal to force of gravity in magnitude and its opposite direction. So when you are stepping into a scale and you are in the elevator moving with constant velocity, then what is the weight that the elevator is telling you, or sorry, the scale is telling you, is the true weight. So this is how much you weigh. However, if we have the second case when the acceleration is going up with a certain value, so I will keep the number the same just for simplicity. So it's going up, then what we have is a different story. So the free body diagram on this case will be something like this. This is force of gravity, which is your mass times acceleration due to gravity. But since it is acceleration is going up, that means that force net will be up as well. So you will have a force normal that is greater than force of gravity. But force normal is directly connected with the force of the spring on the scale. So then this will tell you a higher weight. So this is force of the spring on the scale. So this case will tell you a higher weight on the scale. Make sense? And the third case, when you are moving with an acceleration that is going down, for free body diagram of this situation will be so that the force normal is less than force of gravity in magnitude, because we are saying that the direction of the acceleration is down, which means that force net will have the same direction as the acceleration. So since force normal of the spring of the scale is related with the force of the springs on the scale, then this is going to show that you are weighing less, even though that you are in 1 minute and you are in an elevator. So you will see that when the elevator is going up, your weight will be higher. And as the elevator starts going up, will move with constant velocity, then you will see that the weight will go to your true weight. And when the elevator is going down, as soon as it's starting to go down, then you will see less weight, and until it reaches the point where it is constant again, so that will go to your true weight. Make sense?